Look around you, at the buildings you live in, the roads you drive on, even the water that flows from your tap. So much of our modern world feels like a product of our own time, a testament to steel and silicon. But what if I told you that the ghost of an ancient empire is quietly holding it all together? That the very foundations of our civilization were laid not in the last century, but over 2,000 years ago, by masons and engineers whose names are lost to history, yet whose work still defines our landscape. They built on a scale so grand, with a precision so exact, that their structures have defiantly resisted centuries, earthquakes, and the slow decay of time itself. How is it possible that a civilization without electricity, without powered machinery, without computer-aided design, managed to create monuments that have outlasted entire nations? That question brings us to the heart of a profound historical mystery, one we are about to explore together. It leads us to the sun-baked stones of the Colosseum, where the roar of the crowd is a distant echo, and to the soaring arches of aqueducts marching across the countryside like a stone army. These are not just ruins, they are silent witnesses to a level of ingenuity that borders on magic. The secrets of Roman engineering are not simply a list of techniques. They are a window into a mindset, a philosophy of building for eternity. The Romans didn't just want their structures to stand for a generation. They intended them to last forever, and in many staggering cases, they succeeded. They solved problems of physics and logistics that would challenge us even today. And they did it with little more than brute force, brilliant geometry, and a revolutionary material that changed the world, a form of concrete we still cannot perfectly replicate. So consider this video an invitation to step back in time, to walk alongside those ancient engineers and uncover the brilliant, and sometimes mysterious, secrets they left behind. We are going to pull back the curtain on how they turned ambition into everlasting stone, how they moved mountains of water across vast distances, and how they designed buildings that could hold tens of thousands of people safely. This is a journey into the mind of an empire that saw no limits, a deep dive into the lost knowledge that allowed them to achieve the impossible. By the end, you will never look at a bridge, a road, or a simple brick wall the same way again, because you will see the invisible hand of Rome, a legacy of genius carved not just in stone, but into the very DNA of our modern world. Yet for all their grand designs in stone and arch, the Romans possessed one singular innovation that truly made their impossible dreams a physical reality. It was a material that flowed like a liquid and hardened like stone, a substance that could defy the waves of the ocean and the weight of mountains. This was not the concrete we know today, a material that often crumbles within decades. This was Roman concrete, and its secret recipe was so advanced that it has become one of history's most tantalizing technological puzzles. At its heart was a magical ingredient, a volcanic ash from the region of Pozzuoli near Naples, which the Romans called pulvis putiolinus. They discovered that by mixing this fine, dusty ash with lime and water, they created a mortar of incredible strength. But the true genius was in the final, seemingly counterintuitive step, mixing this concoction with seawater. While we would instinctively avoid salt water to prevent corrosion, the Romans embraced it, triggering a remarkable chemical chain reaction. When seawater seeped into the concrete, it reacted with the lime and volcanic ash to form rare, crystalline minerals. One of these, a mineral called aluminum tobermorite, is the key to the concrete's self-healing ability. As tiny cracks begin to form over centuries, water infiltrates the fissures. This water then reacts with the leftover volcanic material and lime, forming new crystalline structures that effectively fill the crack, welding it shut from the inside. It's a material that doesn't just withstand damage. It actively repairs itself, becoming stronger with age, much like a bone that heals after a break. Modern concrete, by stark contrast, is inherently brittle. Once its steel reinforcements rust and crack, the structure is compromised, leading to the slow decay we see in so many of our modern bridges and buildings. The most stunning testament to this ancient superiority lies not on land, but beneath the Mediterranean Sea. Take the Roman harbor of Caesarea Maritima, constructed by King Herod 200 years ago. While modern concrete piers nearby have deteriorated significantly in just a few decades, the original Roman breakwaters remain intact, submerged in the corrosive saltwater. For 2 millennia, the waves have been pounding these structures, and instead of wearing them down, the seawater has continually fueled the chemical reactions that keep the concrete resilient. Scientists studying samples from these harbors have found that the aluminum tobermorite crystals are still forming, a slow-motion repair process that has no end in sight. This is not a passive material slowly yielding to time. It is a dynamic, living stone in a state of perpetual reinforcement. We are only now, with advanced tools like electron microscopes, beginning to decode the complex nanostructure of this ancient marvel, a humble mixture of ash, rock, and saltwater that has proven to be one of the most durable building materials ever created by human hands. But if Roman concrete was their miraculous material, then the Pantheon in Rome is the ultimate expression of its potential, a building that seems to defy the very laws of gravity. Even today, nearly 1900 years after it was completed, its dome remains the largest unreinforced concrete dome anywhere on Earth. Just stand beneath it. The scale is almost incomprehensible. A perfect hemisphere of ancient engineering soaring 43 meters above you, a distance equal to its diameter. There are no steel beams holding it up, no hidden supports. It is a single, breathtaking shell of concrete that has endured while empires rose and fell around it. The central question, the mystery that has captivated engineers and architects for centuries, is simple. How does it not collapse under its own immense weight? The Romans, being masters of practical physics, understood that the greatest enemy of a dome is the crushing force of its own mass, particularly at the top. Their ingenious solution was a masterpiece of material science and design. They didn't just pour a uniform mixture, they engineered the very fabric of the dome to become lighter as it rose. At the massive base, the concrete is mixed with heavy, dense aggregates like travertine and brick. But as the walls curve inward, the recipe subtly changes. Layer by layer, the builders incorporated lighter materials. In the upper sections, you find porous volcanic stones like pumice and even empty clay pots carefully placed within the concrete matrix. This was a deliberate, calculated lightening of the load, reducing the stress on the lower walls without sacrificing structural integrity. It was a way of cheating gravity, making the top of the dome almost buoyant. Then there is the oculus, the great open eye at the very apex of the dome. While it floods the interior with a dramatic, shifting beam of light, its purpose is far more than spiritual or aesthetic. It is a critical piece of structural engineering. By removing the heaviest, most problematic part of the dome, the keystone at the center, the engineers eliminated a massive point of stress. But they did something even more brilliant. The thick ring of concrete that frames the oculus acts as a perfect compression ring, distributing the forces of the domes weight evenly around its circumference. Think of it like the tension ring on a barrel, holding the staves together. The entire dome is essentially a series of arches all meeting at this central point, and the oculus ring binds them, creating a state of perfect equilibrium. And we cannot overlook the coffers, those beautiful sunken panels that decorate the interior surface. While they add to the grandeur, they are not merely decorative. Each coffer removes a significant amount of material, further lightening the overall structure. More importantly, they act like the ribs of a skeleton, adding rigidity and strength to the concrete shell, much like the corrugations in cardboard prevent it from bending easily. Every single element of the Pantheon's dome, from the choice of aggregate in the concrete mix to the patterns on its ceiling, was a deliberate decision aimed at one goal: achieving eternal stability. It stands as a silent, monumental lesson in engineering, a puzzle we have yet to fully solve, reminding us that the Romans didn't just build structures, they engineered permanence itself. Yet for all the stationary majesty of the Pantheon, the Romans also solved a problem of motion on a staggering scale. They mastered the life-giving flow of water, building highways not for people, but for rivers, directing them across the landscape with an audacity that still seems impossible. Imagine the challenge: supplying a metropolis of over 1 million people in ancient Rome with a constant, reliable source of fresh water. There were no electric pumps, no pressure systems. The only force available was the gentle, unyielding pull of gravity. That single, simple law of physics became the driving principle behind one of history's greatest engineering networks, the aqueducts. These were not merely channels. They were precisely calculated water slides that stretched for dozens, sometimes hundreds of miles, descending at a slope so slight it is almost imperceptible to the human eye. The average gradient was a drop of just a few inches for every mile of length. To achieve this over mountainous terrain and deep valleys required a level of precision in surveying that would be impressive even with our modern satellite technology. The Romans' secret weapon for this monumental task was a deceptively simple-looking instrument called the corybates. Forget complex optics. This was a tool of beautiful, practical genius. Picture a long wooden bench about 6 meters in length, supported by legs at each end. From the top of the bench, a small channel was carved and filled with water. By observing the water level in this channel, surveyors could establish a perfectly horizontal line of sight. But the Romans, ever the problem solvers, had a backup for windy days when the water would ripple. They also attached plumb bobs, weighted strings, to each leg. By ensuring the strings hung parallel to marked lines on the legs, they could double-check their level. With this elegant device, teams of surveyors could painstakingly map a course, ensuring that the water channel would maintain its crucial, gentle downhill slope from its source in a distant mountain spring all the way to the city's reservoirs. A miscalculation of even a fraction of a degree over such a distance would mean the water would either flow with insufficient force or, worse, stagnate and back up. Once the path was set, the real construction began, presenting a new set of obstacles. When the surveyor's straight line met a deep valley, they didn't divert the aqueduct around it. They went straight over. This is where we see the most iconic image of Roman engineering: the soaring arcades of stone arches marching across the countryside. These structures were far more than just bridges. They were elevated rivers. Building them required an immense understanding of load and compression. Each arch was a self-supporting structure, transferring the weight of the water channel and itself down through the piers to the foundation. But the true brilliance was in their uniformity and efficiency. The Romans used wooden frames or centers to construct each arch. Once the keystone was set and the mortar cured, the frame could be removed and reused for the next identical arch, allowing crews to work rapidly along the entire length of the valley. The result was a multi-tiered arcade that could reach staggering heights, like the Pont du Gard in southern France, which stands nearly 50 meters tall, carrying water across a river gorge. It was a testament to turning topographical nightmares into engineering triumphs. And when a valley was too deep or a mountain too solid to go over, the Romans went through. They tunneled through solid rock with a relentless determination that is hard to fathom. Teams of workers, using nothing more than iron picks, chisels, and hammers, would dig from both ends of a mountain, meeting in the middle with astonishing accuracy. To ensure the tunnels maintain the correct gradient, they would dig vertical shafts down from the mountain ridge to the proposed tunnel level at regular intervals. This provided ventilation for the workers and, crucially, multiple points from which to dig horizontally, speeding up the process and ensuring the tunnel stayed on its precise, downward course. The aqueducts were a system of constant flow, a seamless integration of channel, tunnel, and arcade, all working in concert to defy geography. They were the circulatory system of the empire, bringing not just water, but life, public health, and grandeur to its cities, a silent, flowing monument to an empire that refused to be limited by the landscape. And while the aqueducts demonstrate the arch's power to conquer vast distances, this single architectural form was truly the backbone of the entire Roman building revolution. To understand its genius, we have to look at what came before. Most ancient civilizations, like the Greeks and Egyptians, relied on the post and lintel system. Think of Stonehenge or the entrance to a Greek temple, two vertical posts with a horizontal beam or lintel laid across the top. It's a simple and effective method, but it has a critical weakness. The entire weight of the structure above, plus any load it carries, bears down directly on that horizontal beam. The longer the span you want to create, the thicker and stronger that lintel must be to resist bending and snapping under the pressure. There is a natural limit, a point where the stone itself can no longer support its own weight, which is why ancient Greek temples often have forests of closely spaced columns. They were needed to support relatively short lintels. The Roman arch shattered this limitation. Its secret lies not in fighting gravity, but in collaborating with it. An arch is composed of a series of wedge-shaped stones called voussoirs. The central, topmost stone is the keystone, which is often seen as the most important, but in truth, every stone in the arch is vital. When weight is applied from above, instead of creating a single point of failure, the arch cleverly transforms that downward force. The pressure is transferred through the carefully shaped voussoirs, converting it into a lateral or sideways thrust that pushes outwards against the supporting walls or piers. The arch is essentially always trying to fall apart sideways, and it's the job of the sturdy abutments on either side to contain that outward thrust. This means the structure is in a perfect state of equilibrium, with the compressive strength of the stone being used to its maximum advantage. The space beneath the arch remains gloriously open and unobstructed, free from the need for supporting columns. This principle allowed the Romans to think on a scale previously unimaginable. They didn't just stop at single arches. They combined them in brilliant and powerful ways. By placing a series of arches in a row, they created the magnificent arcades we see in aqueducts and amphitheater facades. Each arch supports the ones next to it, creating an immensely strong and stable wall punctuated by large openings. But their most revolutionary innovation was the extension of the arch into the third dimension, the barrel vault. Imagine an arch stretched backwards into a long, continuous tunnel. That's a barrel vault. It allowed them to roof over enormous spaces like the public halls in bath complexes or the corridors beneath amphitheaters. Then, they went even further by intersecting two barrel vaults of the same height at a right angle, creating a groin vault. This ingenious design concentrated the weight down into the four corners of the bay, freeing up the walls for large windows and creating soaring, cavernous interiors that felt both spacious and secure. The ultimate expression of this architectural philosophy is undoubtedly the Colosseum. Its entire exterior is a stacked masterpiece of arches, 3 tiers high, each employing a different style of column purely for decoration, as the arches themselves do all the structural work. This repetitive use of the arch made the construction faster and more economical, while simultaneously creating a skeleton that was both incredibly strong and surprisingly lightweight, allowing it to withstand earthquakes that would have leveled a solid stone structure. From the tiny arch over a doorway to the grand vaults of the Basilica of Maxentius, this single concept enabled the Romans to shape space itself, moving from enclosed, column-cluttered rooms to vast, light-filled public arenas. The arch was more than a shape. It was a tool for defying limits, a key that unlocked the potential for an architecture of grandeur and permanence that would define an empire and inspire the world for millennia to come. This mastery of arches and aqueducts, of domes and concrete, reveals an empire that thought in terms of millennia, but perhaps their most pervasive legacy, the one that physically bound their vast territories together, was something they laid down across the landscape, their roads. We still use the phrase, "all roads lead to Rome," but we often forget the sheer, staggering ambition behind it. This was not a metaphor, it was a statement of engineering fact. The Romans built over 250,000 miles of highways, from the rain-swept hills of northern Britain to the deserts of North Africa. And these were not simple dirt paths. They were sophisticated, multi-layered engineering projects designed to be as permanent as the mountains they crossed. The goal was to allow legions to march rapidly, messengers to travel swiftly, and trade to flow uninterrupted in any season, under any weather. A muddy track would not suffice. They needed a platform that was durable, well-drained, and supremely flat. The solution was a revolutionary approach to road building, a recipe for permanence etched in stone and soil. The secret to their incredible durability lies beneath the surface, in a carefully engineered sandwich of materials. The Romans understood that a road is only as strong as its foundation. They didn't just lay stones on the ground, they prepared the ground itself with meticulous care. The process began by digging a long, shallow trench, the fossa, often as deep as 1.5 meters. This trench was the root of the entire structure. Into this prepared bed, they would lay the first layer, the stadimen. This was a foundation of large, flat stones, sometimes fist-sized, sometimes even larger. These stones weren't just dumped in. They were carefully placed to create a stable, porous base. Their primary job was drainage. By creating a layer of loosely packed rocks, any water that seeped through the upper layers would quickly drain down and away from the road surface, preventing the soft earth beneath from turning into a muddy quagmire that would destabilize the entire structure. Think of it as the road's anchor, preventing it from sinking or shifting over time. On top of this sturdy foundation came the second layer, the rudus. This was a thicker stratum, about 10 inches deep, composed of a compacted mix of smaller gravel, broken pottery, and even rubble, all bound together with a lime-based mortar. This layer served a dual purpose. It created a firm, level bed for the final paving stones, and it added further strength and drainage. The lime mortar was the key here, acting as a weak but effective cement that locked the rubble into a solid, unified mass. This rootless layer was painstakingly rammed down until it was incredibly hard and flat, providing a surface that would not settle or deform under immense weight. It was the road's backbone, distributing the load of traffic evenly across the wide foundation below. The third layer, the nucleus, was the final preparatory stage before the visible surface. This was a much finer mixture of gravel, sand, and quicklime, packed tightly into a smooth, level surface. The nucleus was the precision layer. Its job was to fill any remaining irregularities in the rootis and create a perfectly flat and forgiving bed for the massive paving stones to be laid upon. Without this fine, almost sandy layer, the large stone slabs above might crack or settle unevenly. It acted as a cushion, ensuring that the immense weight of traffic would be transferred smoothly down through the harder layers beneath. Finally, after all this hidden preparation, came the crowning glory, the summum dorsum, or the backbone. These were large, polygonal blocks of incredibly hard stone, like basalt or volcanic rock, carefully cut and shaped to fit tightly together. They were not laid flat like modern bricks. They were often set in a slight convex camber, arching gently upward in the center of the road. This brilliant design feature was for runoff. When it rained, water would flow quickly off the raised center and into the drainage ditches that invariably ran along both sides of the road, keeping the running surface remarkably dry and mud-free. The most famous example, the Via Appia, demonstrates the result of this painstaking process. Stretching from Rome to the port of Brindisi, sections of this road, laid over 200 years ago, are still visible and even usable today. The large, dark basalt stones are worn smooth by countless feet, wagon wheels, and centuries of weather, yet they remain locked together, a testament to the genius of their multi-layered construction. Each layer had a specific, critical function, working in harmony to create a structure that could withstand the relentless punishment of time and traffic. This was not merely a path, it was a permanent installation, a statement that Rome had arrived and intended to stay. The next time you drive on a modern highway that needs repaving after just a few years, remember the Via Appia and consider the profound difference between building for the next budget cycle and engineering for eternity. While the Romans conquered the landscape with their roads and defied gravity with their arches, they also turned their engineering genius toward a more intimate challenge, mastering the very air they breathed. In the frigid depths of a European winter, the idea of walking barefoot on a warm floor or relaxing in a toasty room would have seemed like a fantasy for most ancient peoples. But for the Romans, it was a reality, thanks to a revolutionary and remarkably sophisticated system known as the hypocaust. This was the world's first form of central heating, a hidden network of hot air that transformed dank, cold spaces into luxurious environments of comfort. And its principles were so effective that they wouldn't be matched again for over 1,000 years after the empire's fall. The heart of the system was the hypocaustum, the furnace. But this wasn't a simple fireplace in a room. It was a dedicated, constantly burning firebox, usually stoked by slaves, located outside the building or in a special service area below ground level. The true innovation, however, lay in what they built above it. Instead of placing a solid floor directly on the ground, Roman engineers constructed the floor of the room atop a forest of small, closely spaced brick pillars called pilli. These pillars, typically about 2 feet high, created a hidden underground cavity beneath the entire floor surface. On top of this grid of pillars, they laid the floor itself, a massive slab of concrete and tile known as the suspensory. This raised floor was the first critical component, a giant thermal plate waiting to be heated. The hot gases and smoke from the furnace would be channeled directly into this subterranean chamber, where they would swirl and circulate, transferring their heat directly upward into the thick concrete slab above. The floor itself would become wonderfully, evenly warm to the touch, radiating heat steadily into the room. But the ingenuity didn't stop at the floor. The Romans understood that heat rises, and they developed a way to capture that rising warmth and channel it for even greater effect. Within the walls of the most advanced installations, particularly in the caldarium or hot room of a public bath, they built a second circulatory system. They constructed the walls with hollow rectangular terracotta tubes, called tubuli, which were stacked vertically and sealed together. The hot air that had heated the floor cavity would naturally rise, drawn into these tubular channels within the walls. As it traveled upwards, it would heat the clay tubes, which in turn radiated warmth into the room from the sides as well as from below. This created a truly enveloping heat, a sauna-like environment where every surface contributed to a consistent ambient temperature. In some of the grandest villas, these tubuli would even channel the heat up through the walls to heat second-story rooms, a breathtaking feat of thermal engineering. The entire system was a masterpiece of controlled airflow and thermodynamics. The heat needed somewhere to go, and the Romans provided a carefully designed exit. Small, decorative flue pipes, often integrated into the roof tiles or emerging as decorative chimneys on the roof, created a steady draft. This draft was the engine of the hypocaust, constantly pulling the hot air from the furnace through the floor cavity, up through the wall tubes, and safely out of the building. This constant circulation prevented the dangerous buildup of smoke and gases while ensuring a continuous supply of fresh heat. The result was an efficient, whole building heating system that could maintain comfortable temperatures in massive spaces like the immense public baths, which were central to Roman social life. To step into the caldarium of the baths of Caracalla, with its soaring ceilings and vast marble halls, and feel a pervasive, gentle warmth emanating from the very floors and walls, would have been a sensory experience bordering on the miraculous, a powerful demonstration of an empire that could command not just stone and water, but fire and air itself. Now, all of these engineering triumphs of the roads, the aqueducts, the heated baths converged in a single, spectacular monument that served as the empire's ultimate stage for entertainment and social control, the Colosseum. While its iconic facade of arched tiers is instantly recognizable, the true genius of this structure lies not in what you see, but in what you don't. It was a machine for managing crowds and spectacle on an unprecedented scale, and its secrets are hidden in plain sight. Take those 80 archways that punctuate its exterior. To the casual observer, they are simply architectural features, but to a Roman engineer, they were the key to a logistical miracle. These were the vomitoria, a term derived from the Latin word for to spew forth, and they lived up to their name with stunning efficiency. The design was a masterpiece of crowd dynamics. A series of radial corridors, like the spokes of a wheel, led from these exterior arches directly inward to the seating areas. Staircases then branched off, guiding spectators to their designated sections on different levels. This meant that a person entering through a specific arch, guided by a ticket system, could flow directly to their seat without crossing paths with the main streams of people heading to other sectors. There were no dead ends, no bottlenecks. The entire system was designed for one-way, uninterrupted movement. This brilliant planning allowed all 50,000 spectators to be seated in under 15 minutes, and perhaps more impressively, for the entire arena to be emptied in less than 10. It was an ancient version of modern stadium design, ensuring that the experience began and ended with a sense of effortless order, a powerful display of Roman organizational prowess. But if the vomitoria managed the flow of the audience, the true heart of the spectacle lay beneath their feet, in a dark, chaotic world known as the hypogeum. This was the Colosseum's backstage, a vast underground labyrinth of tunnels, chambers, and cages that transformed the arena floor into a dynamic and unpredictable stage. When the Colosseum first opened, the hypogeum did not exist. Early games often featured elaborate flooding for mock naval battles, but the Romans soon covered these basins, constructing a two-level subterranean complex that became the engine room of the games. This network housed everything needed for the spectacle: gladiators preparing for combat, exotic animals like lions and elephants confined in pens, and stagehands ready to create surprising special effects. The hypogeum was a city beneath the city, a place of intense anticipation, fear, and brutal practicality. The most astounding feature of this underground world was its system of primitive elevators and ramps, a marvel of pulley and capstan technology. Dozens of vertical shafts ran from the depths of the hypogeum directly up to trapdoors in the wooden arena floor above. Cages containing animals or platforms holding gladiators would be winched up these shafts using a system of ropes and counterweights, powered by teams of slaves turning large capstans. This meant a lion could appear to magically materialize from nowhere in the center of the arena, or a group of fighters could be dramatically revealed to the roaring crowd. The element of surprise was a key part of the entertainment, and these elevators allowed for a constantly changing theatrical experience. The Romans could stage elaborate hunts, or venations, where a variety of beasts would pop up from different points across the floor, creating a dynamic and dangerous chase. The hypogeum was not a static basement. It was a dynamic machine that brought the underworld to the surface on command. Connecting all these elevators and chambers was a warren of service tunnels, allowing for the seamless movement of people, animals, and equipment out of sight of the audience. There were even connections to nearby buildings, such as the Ludus Magnus, the gladiatorial training school, so fighters could be brought in discreetly. The entire operation required precise timing and coordination, a backstage ballet of stage managers, animal handlers, and technicians working in the semi-darkness to deliver a flawless performance above. The arena floor itself was covered with sand to absorb blood, and it was riddled with these trapdoors and hidden entrances, making every moment unpredictable. The Colosseum, therefore, was a building of two starkly contrasting realities: the sun-drenched, orderly seating for the citizens, and the shadowy, mechanized labyrinth below where the brutal mechanics of the spectacle were managed. It stands as the ultimate synthesis of Roman engineering principles, architectural grandeur, logistical brilliance, and a formidable, almost terrifying, command over both the human and natural worlds to create an experience that was as efficiently organized as it was violently spectacular. From the precisely engineered chaos of the Colosseum, we now journey to the rugged hills of northwestern Spain, to a landscape that looks less like the work of humans and more like a scene from another planet. Here, at a place called Las Medulas, the Romans demonstrated that their engineering prowess wasn't just about creation. It could also be harnessed for controlled destruction on an almost unimaginable scale. This was not a project of building up, but of tearing down, where the primary tool was not a chisel or a trowel, but water itself. The Romans came to these mountains for one reason: gold. Buried within the reddish clay and soft sandstone were rich placer deposits, but extracting them using traditional methods would have been a slow, back-breaking process for centuries. Never a people to choose the slow path when a faster, more audacious one was available, Roman engineers devised a method so powerful and so devastatingly effective that it literally reshaped the terrain. They called this technique ruina montium, the wrecking of the mountains. The entire operation relied on a simple principle of physics: the irresistible force of moving water. But to wield that force as a tool, they first had to master its supply on a colossal scale. The first step was not digging, but damming. Using the same surveying skills they applied to their aqueducts, engineers identified streams and rivers in the surrounding higher elevations of the Montes Aquilanos. They then constructed an extensive network of canals, some stretching over 60 miles in length, to capture this water and channel it toward the mining area. These canals, carved directly into the mountain slopes, were feats of endurance in themselves, maintaining a gentle, consistent gradient for dozens of miles to ensure a steady, gravity-fed flow. This water wasn't destined for a city's bathhouse. It was being stockpiled for an attack. At strategic points above the gold-bearing mountains, the Romans built massive reservoirs, holding millions of gallons of water, creating a potential energy bomb waiting to be unleashed upon the landscape below. The true genius and the terrifying spectacle began deep within the mountains themselves. Before a single drop of water was released, teams of miners, often slaves and forced laborers, would tunnel deep into the heart of the mountain. They dug a complex web of narrow, vertical shafts and horizontal galleries, following the seams of soft rock that held the gold. This was incredibly dangerous work, performed by candlelight in cramped, unstable conditions. But these tunnels were not just for extraction. They were the fundamental components of the demolition plan. The network was designed to structurally weaken the entire mountain from the inside out, creating a honeycomb of chambers that would make the rock mass unstable and primed for collapse. Once this internal labyrinth was complete, the tunnels were sealed at their exits, turning the mountain into a hollow, pressurized vessel waiting to be filled. Then came the moment of ruina montium. The sluice gates on the high-altitude reservoirs were opened, and the pent-up water rushed down through specially reinforced wooden channels, gathering tremendous speed and force. This torrent was not directed at the mountain's exterior, but was funneled directly into the highest entrances of the tunnel network. With explosive power, the water flooded the internal galleries, filling every cavity and shaft. The tremendous hydraulic pressure, trapped within the weakened rock, acted with overwhelming force. The water sought every crack and fissure, its weight and momentum exerting immense stress on the already compromised stone pillars and walls left standing inside. Within moments, the entire mountainside would succumb. The ground would shudder, and with a roar that must have been heard for miles, a vast section of the mountain would simply collapse in upon itself, sliding down into the valley below in an apocalyptic landslide of mud, rock, and water. The process did not end with the landslide. The resulting chaotic mixture of debris and water, now collected in a vast slurry at the base of the mountain, was where the actual gold recovery began. The Romans channeled this slurry through a series of sluices and settling tanks. The heavier gold particles, freed from their rocky prison by the colossal force of the collapse, would settle out in these carefully designed channels, while the lighter waste material, the sterols, was washed away. It was a method of staggering efficiency, allowing the Romans to process enormous volumes of ore in a single catastrophic event. The environmental impact, however, was permanent. The landscape of Las Medulas today, with its surreal, jagged red peaks and deep, lush valleys, is the direct result of this brutal process. It is a beautiful, haunting monument to Roman ambition, a place where the pursuit of wealth led to the literal dismantling of nature itself, proving that their engineering vision encompassed not only the art of creation, but also the calculated power of annihilation. If the audacious destruction of Las Medulas shows the Romans' power to reshape the land, their harbor engineering reveals an equally bold ambition to defy the sea itself. For an empire built on trade and military supply lines, safe, deep water harbors were not a luxury, they were a strategic necessity, but the Mediterranean coast often presented a cruel paradox. The very places that offered the best natural shelter were too shallow for large, heavy loaded cargo ships, while the deep water locations were exposed to the punishing waves and storms that could smash a fleet to splinters. The obvious solution, building protective breakwaters out into the deep water, seemed impossible. How do you build a massive, stable stone structure in the churning, unpredictable depths of the open sea? The answer, once again, lay in a secret of Roman concrete, but this time in a revolutionary application that allowed them to build not just on the water, but within it. The challenge was fundamental. You cannot simply drop stones into deep water and expect them to form a stable wall. The action of the waves will scatter them, undermining the structure before it even begins. The Romans needed a way to create a single, monolithic mass on the seabed, a structure that would act as one solid unit against the force of the sea. Their ingenious method was a process known as underwater pouring. First, they would construct a temporary wooden formwork, a huge box or caisson, and carefully sink it into position on the seafloor where the breakwater was needed. This wooden frame defined the shape of the future structure. Then, the real magic began. Instead of trying to place individual stones, they would transport their special volcanic concrete mixture by barge out to the site. This was not a dry mix. It was prepared to a specific, thick consistency. Workers would then literally pour this liquid stone directly into the submerged wooden form. To the astonishment of any observer who didn't understand the chemistry, the concrete did not dissipate into the water like mud. Instead, it sank through the water column in a cohesive mass, settling into the formwork and, critically, actively bonding with the seawater around it. This is where the pozzolana, the volcanic ash from Pozzuoli, performed its greatest trick. Modern Portland cement undergoes a simple setting process with water. It hydrates and hardens. But Roman concrete, when mixed with seawater, underwent a complex chemical reaction called a pozzolanic reaction. The salt water acted as a catalyst, reacting with the lime and the fine silicate particles in the ash to form insoluble crystalline compounds, like the aluminum tobermorite we discussed earlier. This reaction happened even better, and in fact was strengthened by the presence of the salt. So, while the concrete was being poured, it was already beginning its transformation from a slurry into a rock-hard, integral mass. The formwork held the shape until the concrete had set sufficiently, after which the wood could be removed or left to rot away, leaving behind a permanent, seamless block of artificial stone that was chemically fused to its marine environment. The scale of this achievement is perfectly embodied by the harbor of Portus, built by the Emperor Claudius and later expanded by Trajan just a short distance from Rome at the mouth of the Tiber River. Before Portus, Rome's main port was at Ostia. but its river mouth location silted up constantly and was too shallow for the largest grain ships from Egypt and North Africa. Claudius's engineers set out to create a vast, artificial harbor basin safe from both silting and storms. They constructed two colossal curved breakwaters that reached out into the deep water, creating a protected bay. The scale was staggering. The breakwaters were not simple walls. They were massive, wide-based structures built using this underwater concrete pouring technique. Ancient historians describe moles so vast that lighthouses were built upon them, and the main entrance was guarded by a sunken ship that was later encased in concrete to form an additional wave-breaking island. The true test of this engineering came during a violent storm shortly after its completion. According to the historian Tacitus, a fleet of grain ships sheltered inside the new harbor of Portus survived unscathed, while those caught outside in the old Ostia anchorage were destroyed. This event proved the harbor's viability beyond any doubt. Later, Emperor Trajan added an innovative inner hexagonal basin connected by canals, a masterpiece of logistical design that allowed for the efficient unloading and storage of goods before they were shipped upriver to Rome on smaller barges. The concrete breakwaters of Portus did not just sit in the water. They became part of the seabed, their self-healing properties ensuring that the constant assault of waves only made them stronger over time. They created a calm, deep water haven where none had existed before, securing the food supply for the capital of the empire and demonstrating that Roman engineering ambition truly had no boundaries, conquering the last great frontier, the restless sea itself. Yet for all these monumental achievements in concrete and arch, in road and harbor, one fundamental question remains. How did they achieve such impossible precision over such vast distances without a single satellite, laser, or computer? The answer lies not in magic, but in a suite of deceptively simple tools, handheld marvels of wood and bronze that became the extension of the Roman engineer's will. These instruments were the true secret weapon of the empire, allowing them to impose perfect geometry upon the chaotic natural world. The most iconic of these, the tool that literally set the straight path for their civilization, was the groma. Picture a surveyor standing on a patch of empty land, tasked with laying out the route for a road that must run perfectly straight for 50 miles. His most vital tool is a stout staff, and atop it, a cross-shaped metal bracket that can swivel. From the end of each arm of this cross hangs a plumb bob, a simple weighted string. The principle was elegant in its simplicity. The surveyor would set up the groma and rotate the cross until two opposite plumb lines aligned perfectly with a marker stake placed far in the distance. Once this primary line of sight was established, the two remaining plumb bobs, hanging at a 90-degree angle, would instantly define a perfectly perpendicular line. With this, the engineer could mark out the exact width of the road, the right-angled corners of a military camp, or the precise grid of a new city. The groma was the master of the straight line and the right angle, the fundamental building blocks of Roman order. Its limitation was that it worked best on relatively flat ground. For the more subtle challenge of leveling, the Romans turned to an even more ingenious device. That challenge was the lifeblood of the empire, water. Ensuring that an aqueduct channel dropped at a consistent, almost imperceptible slope of just a few inches per mile required a level of accuracy that seems superhuman. The tool that made this possible was the corybates, a name that evokes its function of taking steps or moving along a course. Far from a delicate instrument, the corybates was a study in robust, practical genius. Imagine a wooden bench about 20 feet long, supported by legs at each end. Along the top of the bench, a shallow channel was carefully carved and filled with water. The surface of this water, as we all know, always finds a perfect level by siding along the water's edge, or by using notches carved at either end. The surveyor could establish a true horizontal line. But the Romans, pragmatic as ever, included a brilliant backup system for windy days when the water might ripple. Attached to each leg was a plumb line. The instrument was leveled when all 4 strings hung parallel to matching marks on the legs. With the chorbates set, the crew could then use measuring rods to determine the height difference between its position and the next station along the proposed aqueduct route. By repeating this process mile after grueling mile, they could map a course with a gradient so precise that water would flow with just enough force to reach its destination without stagnating or eroding the channel. It was an instrument of immense patience, turning the gentle pull of gravity into a measurable, controllable force. For the most complex tasks, such as aligning tunnels through mountains or calculating the angles for siege works, Roman engineers employed a more sophisticated tool, the dioptra. This was the closest the ancient world came to a modern theodolite, an instrument capable of measuring both horizontal and vertical angles with remarkable precision. At its heart was a circular metal disc, graduated with degree marks around its circumference. A sighting tube or a simple alidade, a ruler with sighting pins at each end, was mounted on a central pivot, allowing it to rotate across the face of the disc. To measure an angle, the surveyor would sight a distant object through the alidade and read the angle from the graduated scale. This allowed for feats of engineering that bordered on the miraculous. When tunneling through a mountain, crews could begin digging from both sides, each guided by dioptra measurements to ensure they would meet in the middle with astonishing accuracy. The same tool could be used to plot the trajectory for a ramp up to a besieged city's walls, or to lay out the elaborate drainage systems for a vast agricultural estate. While more complex and expensive than the groma or chorbates, the dioptra represented the pinnacle of Roman surveying technology, a testament to their understanding of geometry and their relentless drive to quantify and conquer their environment. The true brilliance of these tools, however, lay not in their individual complexity, but in their collective simplicity and reliability. They were built to be used in the field by soldiers and engineers in dust, rain, and mud. They required no delicate calibration beyond a steady hand and a keen eye. Their power was that they translated abstract mathematical principles into physical, actionable guidance on the landscape. With a groma, a chorbates, and a dioptra, a small team could imprint the orderly mind of Rome onto any terrain, from the deserts of Africa to the forests of Germania. They are a humble reminder that grand visions are built not just with grand materials, but with humble tools wielded by brilliant, determined minds. The soaring arch, the flowing aqueduct, the arrow straight road, all began with the unwavering line of a plumb bob and the still surface of water in a wooden trough. Yet even as they mastered the grand scale of construction and logistics, the Romans also applied their engineering cunning to the grim and intimate realities of warfare. And one of the most chilling examples of this lies not on an open battlefield, but buried deep beneath the sands of a frontier outpost. Our story shifts to the strategic banks of the Euphrates River, to the fortified city of Dura Europos. In the middle of the 250s, this Roman garrison found itself besieged by the powerful Sasanian Persian army. The Sasanians, determined to breach the city's defenses, employed a classic tactic of ancient siegecraft. They began digging a mine tunnel aimed directly at the foundation of one of the city's main defensive towers. Their goal was to undermine the wall, causing it to collapse and create a breach for their soldiers to storm through. The Roman defenders, discovering this threat, did what any competent army would do. They started a countermine. They dug their own tunnel directly towards the Sasanian one, intending to intercept the enemy sappers and engage them in the claustrophobic darkness of a subterranean fight. What happened next, however, was anything but a typical underground skirmish. It became an event so bizarre and lethal that it would lay buried as a silent mystery for nearly 18 centuries. The truth of that day began to emerge in the 1930s, when archaeologists excavating the ruins of Dura Europos made a grisly and perplexing discovery. They found the perfectly preserved tunnel frozen in time. Just inside the Roman countermine, they uncovered the remains of 19 Roman soldiers, their bodies stacked in a chaotic pile as if they had died instantly while trying to retreat. A short distance away, at the tunnel's junction with the Sasanian mine, lay the body of a single Sasanian soldier, clad in full armor. For decades, the scene was interpreted as evidence of a fierce, hand-to-hand struggle in the tunnel. But the evidence simply didn't add up. Why were all the Romans found at one end, seemingly overcome before they could even fight? Why was there only one Persian, positioned as if he had been advancing? And most puzzling of all, there were no visible wounds on the skeletons to indicate death by sword, spear, or arrow. These men did not die in combat. They were killed by something far more insidious. The key to unlocking the mystery was found in the very soil surrounding the bodies. Chemical analysis of the archaeological deposits revealed high concentrations of two specific substances: sulfur crystals and bitumen, a thick, tar-like petroleum. We know from historical sources that the Romans were well aware of the noxious properties of these materials. When burned together, sulfur and bitumen create a dense, poisonous cloud of sulfur dioxide gas. This gas is a brutal pulmonary agent. When inhaled, it reacts with the moisture in the lungs to form sulfuric acid, leading to a horrific death by suffocation and internal chemical burns within minutes. The archaeological evidence paints a terrifyingly clear picture of what transpired in that dark tunnel. The Roman soldiers, armed with swords and shields, advanced to meet the Persian sappers. But the Persians were prepared. As the Romans approached the junction, the Sasanians ignited a pre-prepared brazier or a fire pot containing a mixture of sulfur and bitumen. They may have used bellows to drive the lethal fumes directly into the Roman tunnel. The Romans, trapped in the confined, unventilated space, would have had no warning and no escape. The invisible cloud of sulfur dioxide gas would have swept over them, searing their lungs. They would have collapsed in agony, their bodies piling up as they desperately tried to flee from a weapon they could not see or fight. The single Sasanian soldier found at the junction was likely the one who ignited the mixture, perhaps overcome by the fumes himself before he could retreat to safety. This was not a chance event. It was a deliberate, calculated use of chemistry as a weapon. The Sasanians had turned the Romans' own counter-mining tactic into a death trap. This incident at Dura Europos stands as the oldest known archaeological evidence of chemical warfare, a brutal innovation that demonstrates how the science of engineering could be twisted to create horrors far beyond the simple clash of steel. It reveals that the ancient world's pursuit of technological advantage extended into realms we often consider distinctly modern, a dark testament to the timeless nature of ingenuity in the art of war. This discussion of chemical warfare reveals a dark facet of Roman-era ingenuity, but it also highlights their profound appreciation for technology, whether homegrown or acquired from their rivals. And this brings us to one of the most tantalizing and controversial artifacts ever pulled from the sea, an object that seems to defy our entire understanding of ancient technological capability. In the year 900, sponge divers exploring a Roman-era shipwreck off the coast of the Greek island of Antikythera made a discovery that was initially overshadowed by the statues and jewels they recovered. It was a lump of corroded bronze, encrusted and crumbling, that sat in a museum storage room for months before anyone noticed it had broken apart, revealing something astonishing inside: a complex system of interlocking bronze gears, precisely cut and arranged in a way that resembled nothing less than a mechanical clock. But this was no clock from the Renaissance. It had been lying on the seabed for over 2,000 years. This was the Antikythera mechanism, and it has been called the world's first analog computer. The immediate and most persistent question is one of origin. The ship that carried it was Roman, a massive freighter laden with Greek treasures, likely bound for a triumphant parade in Rome sometime around the 1st century before the Common Era. But did the Romans build this marvel, or were they merely transporting it as a priceless spoil of war? The inscriptions on the device itself are in Greek, and its astronomical calculations are based on Greek models, strongly suggesting it was created within the Greek world, perhaps on the island of Rhodes, a known center of astronomical and mechanical innovation. The great thinker Archimedes, a century earlier, was said to have built complex planetaria, and this device seems a direct descendant of that tradition. The prevailing theory, therefore, is that the Romans, having conquered the Greek world, recognized the immense value of this object and were shipping it home as the ultimate trophy, a symbol of their domination over a sophisticated culture. But what if there's another possibility? What if the Romans were not just passive transporters, but active participants in this level of technological sophistication? We know the Romans were brilliant practical engineers, masters of applied geometry and mechanics in their aqueducts and siege engines. The Antikythera mechanism, however, represents a different kind of genius: theoretical, mathematical, and miniaturized. It's a leap from building a massive arch to fabricating a gear train with teeth cut at precise angles to simulate the irregular motions of the heavens. There is no archaeological evidence of the Romans producing anything else of similar mechanical complexity, yet they clearly understood and valued its function. This wasn't a mere decorative item. It was a sophisticated scientific instrument. Could a civilization capable of such breathtaking engineering on a grand scale have also been experimenting with microengineering, perhaps under the guidance of Greek scholars who were now part of their empire? The shipwreck date places the mechanism squarely in a period when Rome was absorbing Greek knowledge voraciously. It's not impossible that a workshop in a city like Alexandria or Rome itself could have been attempting to replicate or even improve upon Greek designs. To understand why this device is so revolutionary, we need to look at what it actually did. For decades, using advanced imaging techniques like X-ray tomography, scientists have been able to peer inside the corroded fragments and decipher the inscriptions. The mechanism was a hand-cranked, geared calculator of stunning complexity. By turning a knob on the side, a user could advance the gears to display the positions of the sun, moon, and likely the 5 known planets on a dial. It could predict lunar and solar eclipses with remarkable accuracy. It even accounted for the moon's elliptical orbit, using a clever pin and slot device that introduced a subtle variation in speed, a level of precision we wouldn't see again until the 14th century. One of its most fascinating features was a dial that tracked the 4-year cycle of the Panhellenic Games, the ancient equivalent of the Olympics, making it not just a scientific tool, but a social and cultural calendar. It was, in essence, a portable mechanical model of the universe as the Greeks understood it. The existence of the Antikythera mechanism forces us to completely reconsider the technological landscape of the ancient world. It was not a one-off miracle, but proof of a lost tradition of high-precision mechanics. The craftsmanship of its gears is too advanced to be a fluke. It implies a workshop, a lineage of artisans who knew how to cast and cut bronze to tolerances we would associate with 18th century watchmakers. This knowledge vanished, perhaps a casualty of the very wars and instability that brought the mechanism onto that Roman ship. The Romans, for all their practical brilliance, may have prioritized different kinds of engineering. The roads, walls, and aqueducts that sustained their empire over these delicate philosophical instruments. They appreciated the result, the predictive power, but may have lacked the scholarly drive to continue the theoretical work. The Antikythera mechanism thus stands at a crossroads of civilizations. It is a Greek brainchild, a testament to their abstract mathematical genius, but its presence on a Roman ship is a powerful symbol of Roman acquisitiveness and their keen eye for powerful technology. It represents a path not taken, a secret level of ancient science that was lost to the world for a millennium and a half, a ghost of a potential future where the analog computer age began 200 years before it actually did. Now, let us travel from the cosmic calculations of the Antikythera mechanism to the gritty, rhythmic pulse of a different kind of Roman machine, one that was not about predicting the heavens, but about feeding the masses. Tucked away in the sunny countryside of southern France, near the town of Arles, lie the ruins of an industrial complex so advanced for its time that it feels like a relic from a much later age. This is the Barbagal water mill, and it stands as a stunning and often overlooked testament to the Roman capacity for large-scale industrial automation. While we marvel at their monuments and aqueducts, this facility reveals a practical, almost modern genius for mass production. It wasn't built for glory or spectacle. It was built to solve a fundamental problem. How you feed a bustling, growing city without relying on the slow, back-breaking labor of countless slaves or animals turning millstones by hand. The Romans answered this question with a breathtaking feat of hydraulic engineering that turned flowing water into edible bread. The scale of the Barbagal complex is what immediately staggers the imagination. This was not a single, quaint water wheel beside a stream. It was a factory, carved into a steep hillside. It consisted of 2 parallel rows of 8 water wheels each, making 16 wheels in total, all powered by a single, masterfully designed aqueduct. The aqueduct that supplied the nearby city of Arles was diverted to the top of the hill, where the water was split into 2 channels that ran down the slope, each channel feeding its own row of mills. The genius of the design lay in its cascading efficiency. The water would pour onto the top wheel, turning its massive stones to grind grain into flour. After doing its work, the water wasn't simply wasted. It was channeled down to power the second wheel in the sequence, and then the third, and so on, all the way down the hillside. This sequential use of the same water meant that a single flow of water from the aqueduct could generate power 16 times over, a concept of energy recycling that wouldn't become common again until the Industrial Revolution. The output was staggering. Historians estimate that the Barbagal mills could produce enough flour in a single day to feed the entire population of Arles, which at its peak was around 12,000 people. This was not just a mill. It was the ancient equivalent of an industrial bakery, operating around the clock, fueled by the relentless, free energy of gravity and water. To understand the machinery itself, picture each mill as a self-contained unit. The water from the aqueduct channel would be directed through a wooden chute onto the paddles of a large, vertical water wheel. The force of the falling water would set the wheel spinning, and this rotary motion was transferred through a central axle to the millstone inside the mill building. The Romans used a brilliant piece of engineering called a gear train to solve a crucial problem. The water wheel turned horizontally, but the millstone needed to turn vertically. The axle from the water wheel ended in a gear, which meshed with another gear set at a right angle on a vertical shaft. This shaft, known as a lantern gear, then turned the heavy upper millstone, called the runner, against a stationary lower stone, the bedstone. The grain was fed through a hole in the center of the runner stone, and the grinding action would pulverize it into flour, which would spill out from the edges. The entire process was a continuous, automated loop. As long as water flowed from the aqueduct, the wheels turned, the stones ground, and flour poured out, requiring only a small number of attendants to feed in grain and collect the finished product. The true significance of Barbagal lies in what it represents: a shift from purely manual or animal-powered labor to organized, industrial-scale mechanization. This was an early and powerful example of non-human energy being harnessed for mass consumption. It freed up immense human and animal resources for other tasks and created a reliable, predictable food supply that was less susceptible to the limitations of drought or animal fatigue. The existence of such a complex suggests that the Romans were thinking in terms of industrial output and economic efficiency in a way we rarely attribute to the ancient world. It proves that their engineering brilliance wasn't confined to temples and amphitheaters. It was also applied to the mundane but vital infrastructure of daily life. The rhythmic, pounding sound of those 16 water wheels was the sound of an empire streamlining its very sustenance, a mechanical heartbeat that powered urban life on a scale that wouldn't be seen again in Europe for more than 1,000 years. The ruins at Barbagal are a silent monument to a lost industrial revolution, a secret of Roman practicality that fed cities and demonstrated a level of technological thinking that was, for its time, truly revolutionary. While the aqueducts and roads represent the peaceful infrastructure of the empire, the Roman legions were, at their core, a force of conquest, and their engineering genius was perhaps most terrifyingly displayed on the battlefield. When an enemy city shut its gates, hoping its walls would provide safety, the Roman response was not a simple siege of starvation. It was an orchestrated spectacle of mechanical destruction. They would transform the landscape outside the walls into a bustling workshop, building monstrous machines designed not just to break defenses, but to dismantle the very will of those inside. Two of the most iconic of these engines were the battering ram and the siege tower, but to think of them as simple tools is to miss the profound engineering secrets that made them so devastatingly effective. Take the battering ram or Ares. In its most primitive form, it was little more than a large log carried by soldiers, but the Roman version was a masterpiece of amplified force and protected application. They mounted the massive ram, often tipped with a hardened iron head shaped like the animal it was named for, within a long, sturdy shed on wheels. This structure, called a vinia or a larger testudo, was covered in fire-resistant materials like raw hides or damp clay. This protective shell was the ram's first secret. It allowed crews to operate the ram continuously, safe from the arrows, stones, and boiling pitch hurled from the walls above. But the true innovation was in the suspension system. The Romans didn't just have soldiers holding the ram. They hung it from the roof of the shed on heavy chains or ropes, creating a giant pendulous weapon. This allowed the crew to swing the ram back and forth with much greater momentum than could be achieved by simply pushing it forward. The weight of the ram did the work, and the suspension acted as a force multiplier, focusing immense energy onto a single point on the wall with each rhythmic, thunderous blow. Some massive rams were so heavy they required crews of 100 men, all working in coordinated rhythm inside their mobile fortress, turning a crude bludgeon into a precision instrument of demolition. Yet the ram was a tool of localized destruction. To truly overwhelm a city's defenders, the Romans needed to get their soldiers onto the walls themselves. This was the purpose of the siege tower, or Helepolis, the taker of cities. These were not simple ladders. They were multi-story wooden skyscrapers, sometimes reaching the height of the walls they were assaulting, and even taller. Building one was a logistical marvel, requiring vast amounts of timber and skilled carpentry under the constant threat of enemy attack. The primary secret to their stability was their immense base. To prevent these towering structures from tipping over, they were built on a wide, stable foundation, often moving on multiple heavy-duty wheels. The lower levels were frequently filled with earth or heavy ballast to act as a counterweight, lowering the center of gravity and making the tower incredibly difficult to topple, even when struck by projectiles or when soldiers massed on its upper levels. This counterweight principle was a critical piece of structural engineering that turned a precarious wooden frame into a stable assault platform. Mobility was the next great challenge. How do you move a building-sized tower, weighing many tons, across rough, often deliberately sabotaged ground towards a heavily defended wall? The Romans employed a system of complex capstans and pulley systems, powered by teams of soldiers or even oxen inside the base of the tower or walking alongside it. Thick ropes would be attached to the tower's frame and wound around these capstans. By turning the capstans, the crews could slowly, inexorably, winch the tower forward. This system provided the controlled power needed to navigate the battlefield. But the approach was still incredibly dangerous. To protect the crews and the tower itself during its advance, the Romans used mobile sheds called vini. These were like the protective covering for the ram, but on a larger scale, creating covered corridors that allowed soldiers to move materials and themselves from the main camp to the base of the tower while shielded from enemy fire. The entire operation was a coordinated ballet of protected movement and immense mechanical effort. The exterior of the siege tower was also a lesson in adaptive defense. The side facing the enemy walls was typically covered with the same fire-resistant hides as the battering ram sheds, but often the Romans would add fresh, uncured animal hides, which were less flammable and could better resist incendiary attacks. Some accounts even describe towers covered with iron plates for added protection. As the tower drew closer, its final secret weapon was deployed, the drawbridge. The top level housed a platoon of elite soldiers, and a hinged ramp was lowered onto the enemy battlements, creating a direct bridge for a storming party. The psychological impact of this moment cannot be overstated. After days or weeks of watching this monstrous wooden fortress creep closer, seeing a bridge slam down and armored legionnaires pour onto the walls was often enough to break the defenders' resolve entirely. The siege tower was more than a machine. It was a weapon of profound psychological warfare, a physical manifestation of Roman inevitability, demonstrating that no wall was high enough and no defense strong enough to stop the relentless engineering might of the legions. From the thundering approach of siege towers to the rhythmic grinding of watermills, Roman engineering consistently demonstrated a mastery of force and form. But perhaps one of their most enduring legacies, one that literally connects the past to the present, is found in their bridges. While we've marveled at the arches of aqueducts, the bridge represents the purest application of this principle, designed not just to carry a trickle of water, but to withstand the immense, unpredictable fury of a river in flood. A Roman bridge wasn't merely a path across a gap. It was a statement of defiance against one of nature's most powerful forces, and the secrets of their longevity are etched into the very stones that still stand today. The first line of defense was always the bridge's foundation, the piers that rose from the riverbed to support the graceful arc of the arches. The Romans understood that a river is not a static enemy. Its current is a relentless, scraping force, and its floodwaters carry debris that can smash a poorly designed support to rubble. Their brilliant solution was the cutwater. Instead of building a simple, rectangular pier, they extended the upstream side of each foundation into a sharp, angular, or semicircular point. This seemingly simple modification was a stroke of hydrodynamic genius. When the river's current hit the pier, the cutwater would cleanly slice through the flow, diverting the water and any logs or debris it carried smoothly around the sides of the structure. This drastically reduced the direct pressure on the pier itself and prevented debris from piling up against it, which could create a dam effect and increase the force of the water catastrophically. On the downstream side, the cutwater was often tapered as well, helping the water reunite without creating turbulent, destructive eddies that could erode the riverbed around the pier's base. It was a design of elegant efficiency, teaching the water how to flow harmlessly around the obstacle. But a sturdy pier is only as strong as the arch it supports, and here, the Romans achieved a level of precision that borders on artistry. The true strength of a Roman arch bridge lies in the perfect fit of its voussoirs, the wedge-shaped stones that form the arc. Each stone was painstakingly cut and dressed to exact specifications, ensuring that when placed together, they created a seamless, interlocking curve. The Romans typically used a slightly rounded or segmental arch rather than a perfect semicircle. This shape had a crucial advantage. It required less vertical height to span the same distance, which meant the bridge's roadway could be flatter and more stable for traffic, and the entire structure presented less of an obstruction to floodwaters. The keystone, the central voussoir at the top of the arch, is often given mythical status, but in reality, every stone in the arch is vital. Once the wooden centering was removed, the weight of the bridge and any load upon it was transformed into compressive force, pushing each stone firmly against its neighbors. The entire arch became a single, monolithic structure in a state of perfect equilibrium, channeling all its weight down through the piers and into the solid ground. The precision of the stonework was so exact that many Roman bridges were built without any mortar at all, relying solely on the perfect fit and compressive force of the stones to hold them together for millennia. No bridge embodies this combination of rugged durability and elegant design better than the Alcantara Bridge in western Spain. Its very name, derived from the Arabic for the bridge, speaks to its enduring preeminence. Completed in the year 106 of the Common Era under the Emperor Trajan, it was a project of such pride that its architect, Gaius Julius Lacer, had an inscription carved into it declaring it will last forever and ever throughout the ages. Over 1900 years later, it is difficult to argue with his confidence. The bridge spans the deep Tagus River gorge with 6 breathtaking arches, the largest of which is nearly 30 meters wide. The piers are monumental, rising from the rock-solid riverbed, their cutwaters still sharp and effective after centuries of seasonal floods. The stonework is a masterpiece of ashlar masonry, with giant granite blocks so perfectly joined that a knife blade cannot be inserted between them. This bridge has not merely survived. It has been in continuous use for almost 2 millennia, supporting everything with Roman legions and carts to modern cars and trucks. It even withstood deliberate attempts at destruction during various wars, with one arch being partially blown up in the 18th century and later meticulously restored. The Alcantara Bridge is not a ruin. It is a living, functioning piece of Roman infrastructure, a silent testament to engineers who built not for their own glory, but for the certainty of a future they would never see. But while Roman bridges conquered rivers and aqueducts tamed distant springs, the greatest challenge often lay not in what they brought to the city, but in what they had to take away. To understand the true foundation of Rome's greatness, we must venture underground into a world of perpetual darkness and flowing filth, to a structure so vital that its name literally means the greatest sewer. This is the Cloaca Maxima, and its story begins not with bricks and arches, but with a swamp. The legendary 7 hills of Rome were not the pristine peaks of our imagination. The valleys between them were low-lying marshlands, flooded regularly by the Tiber River, creating a landscape of stagnant water, disease, and instability. Before Rome could become a city of marble and million, it first had to solve the fundamental problem of its own geography. The earliest solution, initiated by the Etruscan kings around the 6th century before the Common Era, was audaciously simple. They dug a massive, open-air canal, channeling the waters from these marshes and several small streams directly into the Tiber. This initial project was less about sanitation in the modern sense and more about land reclamation. By draining the swampy valleys, particularly the Forum Romanum, they created stable, buildable land right in the heart of the future city. This was the genesis of the Cloaca Maxima, a public works project of such immense importance that it literally created the physical and political center of the Roman world. For centuries, this great ditch served its purpose, but as Rome grew from a town into a metropolis, an open channel running through the city center became a major liability, a source of foul odors, and a dangerous obstacle. The engineering response was to enclose it. This marked the second, and perhaps more brilliant, phase of the sewer's life. Starting around the 3rd century before the Common Era, Roman engineers began the monumental task of vaulting over the entire canal. Using the same principles of the arch that made their aqueducts possible, they constructed a massive stone tunnel. The original open ditch was deepened, and its sides were lined with tightly fitted blocks of volcanic tuff, a stone resistant to water erosion. Then they began to roof it over with a series of immense curved vaults. The construction technique was a marvel of logistics and courage. Workers would build wooden centering to support the arch stones until the keystone was set and the mortar cured. They worked in shifts in cramped, dangerous conditions, gradually transforming the open scar in the landscape into a hidden, subterranean river. The final result was an enclosed conduit so vast that, according to the Roman historian Pliny the Elder, a cart loaded with hay could be driven through it. This vaulting not only contained the stench and removed the physical barrier, but also allowed for the expansion of the city directly above the very land the sewer had helped to create. The true secret to the Cloaca Maxima's longevity, however, was not just its robust construction, but a philosophy of continuous, proactive maintenance. The Romans understood that a sewer left to itself would eventually clog and fail. To prevent this, they appointed officials, the curators cloacarum, whose sole responsibility was the upkeep of the system. Maintenance crews would regularly venture into the depths to clear blockages of debris and silt. But the most ingenious aspect was the use of the sewer system itself as a cleaning mechanism. The Romans deliberately channeled excess water from public fountains and bathhouses in the cloaca. This daily influx of relatively clean water acted as a flushing system, scouring the tunnel's bottom and keeping the waste moving toward the river outlet. They even engineered the slopes of the city's streets to direct rainwater runoff into the sewer mouths, using natural storms to provide periodic, powerful surges that would cleanse the entire network. This was a system designed with its own life cycle in mind, a perfect marriage of construction and perpetual maintenance. The legacy of this ancient engineering triumph is almost impossible to overstate. The Cloaca Maxima did more than just carry away waste. It was the unsung hero of public health. By removing standing water and sewage from the city streets, it helped control the spread of waterborne diseases, allowing the population to grow to densities that would have been impossible otherwise. It enabled the development of multi-story apartment buildings, the insulae, with their basic latrines, because there was now a system to carry the waste away. Most symbolically, by draining the Forum, it created the stage upon which the drama of the Roman Republic and Empire would unfold. Every law debated, every triumph celebrated, every speech given in that central space happened on ground made stable and dry by the hidden river flowing beneath it. The Cloaca Maxima is a powerful reminder that the grandest achievements of civilization are often built upon the most humble and essential foundations. It remains in use to this day, a silent, enduring testament to the pragmatic genius that understood that a city's greatness is measured not only by its temples and palaces, but by the strength of what lies beneath. The legend of Nero's revolving dome stands as one of history's most tantalizing technological mysteries, a story that seems to blur the line between imperial extravagance and impossible engineering. After the Great Fire of Rome in the year 64, Emperor Nero seized the opportunity to construct his vast pleasure palace, the Domus Aurea, or Golden House. Ancient historians like Suetonius and Tacitus describe a dining room of almost surreal opulence, but it's the account from the biographer Suetonius that captures the imagination most vividly. He wrote of a principal dining hall with a revolving ceiling, one that mirrored the motions of the heavens, turning slowly day and night, scattering flowers and perfumes upon the guests below. At first glance, this sounds like pure poetic exaggeration, a metaphor for Nero's god-like aspirations. But what if we take the Romans at their word? What engineering secrets could have made such a fantastical feat possible in the 1st century? The most plausible theory points to a mechanism powered by the one force the Romans had already mastered for large-scale industry: flowing water. We know from the archaeological record at places like the Barbagal Mill complex that the Romans were experts at harnessing water power for continuous rotary motion. A revolving dome would have required a consistent, smooth, and powerful source of energy. The Domus Aurea was built on a hill with complex water features, including an artificial lake and sophisticated plumbing. It is entirely conceivable that engineers diverted a steady stream of water from an aqueduct to turn a large, hidden water wheel situated beneath the dining room floor. This wheel could have been connected through a series of gears to a central pivot, slowly rotating the entire ceiling structure. The challenge would have been immense, managing friction, ensuring the structure above was perfectly balanced, and preventing leaks into the lavish space below. But these were the same engineers who built the Pantheon's dome and the aqueducts. The principle was within their grasp, even if the execution would have been phenomenally complex. Another compelling possibility involves a system of counterweights and manpower, a solution less elegant than water power, but perhaps more reliable for a controlled, intermittent spectacle. Instead of a continuously rotating dome, the room might have featured a rotating platform for the diners themselves. Imagine the entire floor of the dining area, with Nero's couch at its center, mounted on a massive, low-friction bearing, perhaps a large pivot stone set in a bronze socket, similar to the mechanism used for rotating heavy siege towers. Teams of slaves, hidden in a chamber below, could have pushed on long spokes radiating from the central pivot, slowly turning the platform. From the perspective of the guests seated on this revolving floor, the ceiling, decorated with stars and celestial patterns, would have appeared to be moving around them. This clever trick of relative motion would have created the illusion of a revolving universe without requiring the immense effort of moving the entire roof structure. The reported scattering of flowers and perfumes could have been accomplished through simple holes in the stationary ceiling above, timed to release their contents as the rotating platform passed beneath. Ultimately, the truth remains buried, both by the passage of time and by deliberate action. After Nero's death, his successors sought to erase the Domus Aurea from memory. The vast palace was stripped of its valuables, filled with earth, and built over. The baths of Trajan were constructed directly on top of its remains, which ironically helped preserve many of its underground chambers. Modern archaeologists have uncovered breathtaking frescoes and vaulted rooms, but no definitive evidence of a revolving mechanism has been found. This absence fuels the skepticism. Could the entire story be a misunderstanding? The ceiling might have featured an intricate, stationary mosaic depicting the constellations, with cleverly placed lamps that were moved by servants in a hidden attic space to simulate the passing of the sun and moon, creating a celestial light show that was described in awe-struck terms as a revolving dome. Whether myth or reality, the legend of Nero's revolving dining room serves a profound purpose. It represents the absolute pinnacle of Roman engineering ambition, a point where practical skill met limitless imagination. Even if it was never built, the fact that such a concept was seriously discussed and credited to their engineers tells us something crucial about their capabilities and their reputation. They lived in a world where the impossible seemed merely a technical challenge. The revolving dome is the ultimate symbol of an era that poured concrete underwater, heated entire buildings with hollow walls, and plotted aqueducts across mountain ranges. It challenges us to reconsider the limits of ancient technology and to wonder what other breathtaking secrets still lie hidden, waiting for a trowel or a curious mind to bring them back into the light. But for all their grand achievements in stone and concrete, the Romans were also masters of a more delicate art, glassmaking. They produced stunning vessels, mosaics, and windows, yet lurking in the historical record is a tantalizing account of a discovery so revolutionary it threatened the very foundation of the empire's economy. This is the strange tale of vitrum flexile, or flexible glass, a story that blends technological possibility with imperial paranoia. The primary source is the Roman historian Pliny the Elder, and later retellings by Cassius Dio and Petronius, who recount an incident during the reign of Emperor Tiberius. According to the story, an unnamed inventor, a humble glassblower, presented the emperor with a unique gift, a drinking bowl made entirely of glass. What made this bowl extraordinary was its property. After Tiberius examined it, the inventor, perhaps seeking to prove its authenticity, deliberately dropped it on the stone floor. Instead of shattering into 1,000 pieces, the bowl merely dented. The inventor then calmly took out a small hammer and proceeded to beat the dent back into shape, leaving the vessel as good as new. This demonstration of what appeared to be unbreakable, malleable glass should have earned the man immense wealth and honor. Instead, it sealed his fate. Pliny writes that Tiberius's first question was a chillingly practical one. Had the inventor shared the secret of this flexible glass with anyone else? Upon hearing that the artisan was the sole keeper of the formula, the emperor, fearing that this new material would render gold and silver worthless and thus collapse the Roman economy, ordered the man's immediate execution. His workshop was allegedly destroyed to ensure the secret died with him. On the surface, this is a classic fable about the dangers of innovation threatening the established order. But for historians and materials scientists, it presents a fascinating puzzle. Was this merely a moralistic myth, or could there be a kernel of truth buried within? What material, known to the ancient world, could have behaved in a way that was accurately described as flexible glass? Modern science offers several compelling possibilities that transform the story from pure legend into a plausible, misinterpreted technological event. The most likely candidate is not glass as we know it, but a highly ductile metal. The ancient world was familiar with many alloys, and one in particular stands out for its glass-like appearance and remarkable malleability, a specific type of pewter or a white bronze. If an artisan had developed a particularly brilliant, silvery alloy and polished it to a high, reflective sheen, it could easily have been mistaken for glass by an observer, especially when crafted into a vessel. The properties described in the story being dented and then hammered back into shape are perfectly consistent with the behavior of a soft metal. The inventor may have been a clever metallurgist attempting to pass off his durable metal cup as a miraculous glass one, a spectacular trick that backfired catastrophically when the emperor took the deception at face value and saw it as an economic threat. Another intriguing theory points to the known existence of ancient plastics. The Romans were adept at working with natural resins and polymers, such as amber and bitumen. It is conceivable that an artisan discovered a way to create a transparent or translucent resin-based material that was flexible and shatter-resistant. While this would not have been true silicate glass, its appearance could have been convincingly glass-like. A bowl made from such a substance would indeed dent rather than break, and might even allow for some reshaping. This explanation bridges the gap between the literal description of the material and known Roman chemical expertise, suggesting the inventor had stumbled upon a form of early plastic, a material whose true nature was so unfamiliar that it could only be described in the terms they knew, as a strange type of glass. Perhaps the most scientifically fascinating possibility involves the actual structure of glass itself. While standard glass is brittle, certain modern materials like metallic glass or advanced polymers can exhibit flexibility. These materials require incredibly rapid cooling from a liquid to a solid state, a process that prevents the atoms from arranging into a rigid crystalline structure, leaving them in a more amorphous and potentially less brittle state. While it is almost impossible to imagine a Roman artisan achieving the precise conditions necessary for creating a true flexible glass through ancient furnace technology, the story could be a distorted memory of a rare and accidental discovery. An unusual batch of ingredients, a specific type of sand, or a unique quenching process might have resulted in a glass object with unusual toughness, one that bent slightly under stress before breaking, an event so miraculous to its witness that its properties were exaggerated in the retelling into full malleability. The enduring power of the Vitrum flexile legend lies not in its historical accuracy, but in what it reveals about the Roman mindset. The story demonstrates a keen awareness of the disruptive potential of technology. Tiberius's reaction, whether factual or fictional, reflects a very real understanding that an empire's wealth was tied to the perceived value of its precious metals. A material that could mimic the beauty of glass while possessing the durability of metal truly had the power to destabilize markets. This anecdote serves as a poignant reminder that for all their engineering brilliance, the Romans were still bound by the economic and social structures of their time. It paints a picture of a world where a single invention could be seen as either a marvel or a threat, where the line between genius and treason was as fragile as the very glass the story seeks to describe. The lost secret of flexible glass remains one of history's most intriguing what-ifs, a ghost of a potential material revolution that was, according to legend, extinguished before it could even begin. Building and perfecting the aqueduct's course was only half the battle. The true engineering challenge was maintaining the purity and pressure of that water over centuries. A channel clogged with silt or choked by leaves would render the entire monumental structure useless, and a crack in the lining could drain an entire city's water supply into the earth. The Romans understood that their aquatic lifelines required constant, vigilant care, and they engineered a hidden world of maintenance right into the fabric of the aqueducts themselves. Tucked away from public view, often running parallel to the main water channel, were narrow, secret passageways known as the specus. These were not for water, but for the men who served it. Imagine an Aquarius, a Roman water engineer, carrying a lantern into the dim, echoing darkness of one of these service tunnels. His job was one of meticulous inspection. He would walk the length of the channel, his eyes scanning the arched ceiling and the smooth cement, lining for any signs of cracking or mineral buildup. The specus provided direct access to the channel at regular intervals, allowing crews to descend and perform the essential, messy work of cleaning. Over time, even the fastest flowing water would deposit a layer of sediment and a crusty, limestone-rich deposit called sinter. If left unchecked, this buildup would gradually reduce the channel's capacity and slow the water's vital flow. Teams of workers would regularly scrape the walls and floor, ensuring the channel remained smooth and unobstructed, a never-ending task to preserve the hydraulic efficiency of the system. But the Romans were masters of proactive problem-solving. They knew it was far better to trap debris before it entered the main channel than to constantly clean it out. This is where another brilliant innovation came into play: the piscini limeri, or sedimentation tanks. Positioned at strategic points along the aqueduct's route, often just after the source or before a major urban distribution point, these were large, calm holding basins. The principle was simple yet profoundly effective. As water flowed from the fast-moving channel into the wide, quiet pool of the piscina, its speed would drop dramatically. In this placid environment, heavier particles of sand, silt, and organic matter, which had been swept along by the current, would suddenly lose their momentum and sink to the bottom of the tank. The cleaner water, now freed from its burden of abrasive sediment, would then flow out through an outlet positioned higher up on the opposite side, continuing its journey to the city while leaving the sludge behind. These tanks were designed with cleaning in mind. featuring drains at the bottom that maintenance crews could open periodically to flush out the accumulated muck. Some piscinae were even elaborately decorated, serving as beautiful, functional way stations that ensured the water arriving in Rome was not just abundant, but remarkably clear and pure. Overseeing this entire hydraulic empire was a highly skilled and respected professional class, the aquarii. These were far more than simple maintenance men. They were the civil engineers, plumbers, and water quality experts of their day. Organized into a formal corps, the aquarii were responsible for every aspect of the water supply, from the mountain springs to the public fountains. Their knowledge was both practical and theoretical. They had to understand the principles of gradient and pressure to diagnose flow problems, and they possessed an intricate knowledge of the sprawling network of pipes and distribution tanks within the city itself. Using a complex system of lead and ceramic pipes, and controlled by bronze stopcocks and valves, the aquarii carefully allocated water, prioritizing public health by ensuring a constant flow to public baths and fountains, while also supplying the private homes of the wealthy who paid for the privilege. They were the guardians of public health, constantly monitoring the water's quality and fighting a continuous battle against illegal taps and diversions, a common problem in a city where water was wealth. The work of the aquarii was a testament to the Roman understanding that the greatest engineering marvels are not just built, they are sustained. Their relentless, hidden labor ensured that the miracle of flowing water, delivered from dozens of miles away, remained a reliable, everyday reality for the people of Rome, a silent triumph of maintenance that was every bit as impressive as the construction of the aqueducts themselves. Now, we must venture north from the sunny Mediterranean to the wild, unpredictable waters of the English Channel, where one of the most audacious and secretive military engineering projects in history was about to unfold. The year is 43 of the Common Era. The Emperor Claudius, a man often underestimated by history, has set his sights on the mysterious, fog-shrouded island of Britannia. For the Roman legions, the invasion itself was a formidable challenge, but the true nightmare began the moment they landed. Unlike the friendly coasts of Gaul, Britain offered few natural harbors, and its shoreline was a mix of shallow, shifting sands and steep, exposed beaches. An army of 40,000 men, along with its thousands of horses, siege engines, and months of supplies, cannot simply be dumped onto a beach. Without a secure port to unload heavy equipment and ensure a steady flow of reinforcements and provisions, the entire invasion force would be stranded, vulnerable to attack, and at the mercy of the elements. The conquest of Britain would fail before it even began, not on the battlefield, but on the logistical impossibility of supply. Claudius and his generals understood this fatal weakness, and they devised a solution so radical it seems to belong to a much later era. They would not rely on finding a harbor, they would bring one with them. This was the genesis of a project shrouded in such secrecy that even today, its full details are debated by historians. The goal was to construct a massive, prefabricated harbor complex on the far side of the channel, a portable port that could be towed across the sea and assembled on the enemy shore. Imagine the sheer scale of the ambition. This was not a few small jetties. Contemporary sources, though fragmentary, suggest a structure of immense proportions, a testament to Roman confidence in their maritime engineering. The technology likely involved a combination of massive wooden caissons and floating pontoons. Enormous, hollow wooden boxes, essentially giant barges, would have been constructed in the sheltered ports of Gaul. These caissons were not designed for a gentle voyage. They had to be sturdy enough to survive the turbulent channel crossing while being towed by fleets of oared warships and transport vessels. Once the invasion beaches were secured, perhaps near modern-day Richborough in Kent, these prefabricated modules would be maneuvered into position. The next step was one of breathtaking audacity. The Romans would deliberately scuttle these giant barges, sinking them in a predetermined pattern to form a sturdy, semicircular breakwater. By filling the hollow caissons with rocks and ballast as they settled on the seabed, they created an instant, artificial reef that would protect the inner anchorage from the punishing waves and currents of the channel. This sunken barrier was the first and most critical line of defense, creating a calm lagoon where transport ships could safely unload. But a breakwater alone does not make a harbor. The second component was a network of floating piers and wharves, built upon linked pontoons. These would have been attached to the secured breakwater and extended to the shore, creating a stable platform for the back-breaking work of unloading. Heavy cranes, powered by men on treadmills, could be mounted on these piers to lift artillery, siege towers, and sacks of grain directly from the holds of the ships. This floating infrastructure meant that the Romans could offload their heaviest equipment quickly and efficiently, directly onto the beach, without waiting for the tides or struggling through the surf. It was a system designed for speed and volume, turning a hostile coastline into a functioning logistical hub within days, if not hours, of the initial landing. The entire operation was a masterpiece of pre-planning and modular construction, a concept we associate with modern military engineering, yet executed with Roman practicality 2,000 years ago. The success of this mobile harbor technology was absolute. It allowed Claudius's legions to establish a firm, well-supplied bridgehead that could not be dislodged. From this secure beachhead, the Roman war machine could push inland, its supply lines guaranteed by the artificial port it had brought from home. The remains of what is believed to be this very structure have been identified by archaeologists at Richborough, where massive ditches and timber foundations speak of a major initial fortification and supply base. This innovative approach did not just enable a single campaign, it set a precedent. While the full-scale portable harbor might have been a unique solution for the exceptional challenge of Britain, the principles of rapid, prefabricated construction became a hallmark of Roman military engineering. The ability to build a bridge across the Rhine in days, or to prefabricate the components of a fort for an advancing legion, all stemmed from the same mindset that conceived of a harbor in a box. It was a stunning demonstration that the Roman talent for engineering was not just about permanent monuments in stone, but also about temporary, mobile solutions that could project power across any terrain or any sea with overwhelming efficiency. While the revolving dome and flexible glass speak to Roman ambition, their most terrifyingly effective secrets were often those deployed on the battlefield, where precision engineering meant the difference between life and death. Among the arsenal of siege engines, one weapon stood out for its combination of brutal power and astonishing accuracy: the ballista. This was not a simple catapult that lobbed rocks in a high, arcing trajectory. The ballista was essentially a giant mechanical crossbow, designed to fire a heavy bolt or stone on a flat, direct path with the force of a modern high-powered rifle shot. Its secret, the innovation that set it apart from all earlier artillery, lay not in the size of its arm or the weight of its projectile, but in a revolutionary power source hidden within its frame, the torsion spring. The genius of the ballista was its rejection of brute force in favor of stored mechanical energy. Earlier tension-powered weapons, like the Greek feats, relied on the strength of a composite bow, which had clear physical limits. The Romans, drawing on Hellenistic designs, made a critical leap. They replaced the bow arms with two separate wooden arms, each inserted into a vertical bundle of tightly wound cords. These cord bundles were the heart of the machine. They were typically made from animal sinew, particularly from the necks of oxen, or from women's hair, materials chosen for their incredible tensile strength and elasticity. These bundles, known as torsion springs, were housed in sturdy metal-plated frames. When the weapon was loaded, a winch and claw system pulled a bowstring, attached to the ends of the two wooden arms, back along a central slider. This action forced the arms to swing backwards, twisting the sinew ropes within their frames to an extreme degree. The energy required to create this twist was immense, but once achieved, it was stored perfectly within the spring, waiting to be released in an instant. The triggering mechanism was a masterpiece of simple, reliable engineering. The winch would ratchet the slider back until the bowstring was caught by a metal claw, which was itself held in place by a simple pivoting latch. To fire, the artilleryman or librator would use a heavy mallet to strike a quick-release trigger pin. This would knock the latch free, allowing the claw to pivot down and release the bowstring. The moment of release was where the torsion principle proved its superiority. The pent-up energy in the twisted sinew bundles unwound with explosive force, snapping the wooden arms forward. Because the power was generated by the untwisting of the springs rather than the flex of a single bow, the transfer of energy to the projectile was vastly more efficient and consistent. This resulted in a much higher muzzle velocity and a flatter, more predictable trajectory, making the ballista not just a bombardment tool, but a precision instrument. Accuracy was the ballista's true claim to fame, and it was achieved through a level of craftsmanship and calibration that would impress a modern machinist. Every component had to be perfectly symmetrical. The two torsion springs had to be wound with exactly the same tension. If one was tighter than the other, the projectile would veer wildly off course. The wooden arms had to be identical in length, weight, and flexibility. This required meticulous manufacturing and constant adjustment. The ballista's framework often included calibrated scales and adjustment knobs, allowing the crew to fine-tune the torsion for different ranges and projectile weights. A skilled crew could, after a few ranging shots, hit a specific section of a wall or even an individual defender with terrifying regularity. The effect on enemy morale was devastating. Unlike a random hail of stones from a catapult, a ballista bolt arrived with a sharp, sudden crack, often before the target even knew the weapon had been fired. It was the sniper rifle of the ancient world, capable of picking off commanders on the battlements from a distance of well over 300 meters. The ballista's versatility made it a ubiquitous tool in the legionary toolkit. In its larger form, it could hurl stone shot weighing up to 80 pounds to breach fortifications. But its more common use was with massive iron-tipped bolts, 6 feet long and as thick as a spear shaft. These could penetrate shield formations, armor, and even light fortifications. On the battlefield, they were used to break up enemy formations before the legions engaged. During sieges, they were employed as anti-personnel weapons to clear the walls of defenders. Remarkably, ballistae were also used at sea, mounted on the decks of warships to rake enemy vessels with deadly fire before boarding. The principles of the torsion spring were so effective that they were scaled down to create smaller, man-portable versions like the Cheruballistra, which could be operated by a 2-person crew and served as a form of light field artillery. From the grand siege of Masada to the conquest of Gaul, the ballista was a constant and terrifying presence. a silent testament to the Roman understanding that in war, as in peace, the greatest advantage lay not in chaotic force, but in the disciplined, calculated application of power. It was a machine that perfectly embodied the legion's ethos, systematic, relentless, and brutally efficient. Yet for all its functional genius in bridges and aqueducts, the arch also became the Roman Empire's ultimate canvas for storytelling, a massive stone billboard designed not just to withstand the ages, but to speak to them. The triumphal arch, a freestanding gateway of pure celebration, represents the perfect fusion of engineering might and psychological warfare. While its form is an architectural marvel of precise stone cutting and weight distribution, its true power lies in the hidden messages carved into its very skin. Consider the Arch of Titus, which stands eternally atop the Via Sacra in Rome. To the casual observer, it is a beautiful monument, but to a first-century Roman, it was a chillingly detailed newsreel of imperial power, engineered for maximum emotional and political impact. The engineering genius begins with the stone itself. These arches were not built from local, rough-hewn rock. They were often constructed from the most precious and visually striking materials available, gleaming white marble from Carrara or richly colored granite from distant Egypt. The choice of material was the first signal of importance and permanence, but the real secret lies in the precision of the reliefs. The scenes carved into the inner walls, like the famous depiction of Roman soldiers carrying the spoils from the Jerusalem temple, are not flat carvings. They are masterclasses in deep, three-dimensional sculpture. The artists and engineers worked in concert to create scenes of astonishing depth. Figures in the foreground are carved in high relief, almost detaching from the background, while those further back are shallower. This technique, known as alto relievo, creates a powerful sense of movement and realism, pulling the viewer directly into the triumphant procession. The play of Mediterranean sunlight across these deeply carved surfaces would have cast dynamic shadows throughout the day, making the carved figures appear to move, breathe, and march in perpetuity. This was a static stone panel engineered to feel alive. The narrative itself was meticulously crafted propaganda, its sequence engineered to guide the viewer on a psychological journey. As you pass under the Arch of Titus, the story unfolds in a specific, deliberate order. One side shows the beginning of the triumph, the legionaries carrying the sacred menorah, the silver trumpets, and the table of the shewbread from the despoiled temple. This scene is one of overwhelming Roman power and the humiliation of a conquered people. But it is the panel on the opposite side that delivers the ultimate message. Here, Titus himself stands in his chariot, crowned by victory, led by the goddess Roma. The composition is engineered to leave no doubt. The emperor is not merely a successful general. He is divinely sanctioned, a literal god on earth. The arch's spatial design forces you to walk between these two images, physically immersing you in the narrative from plunder to deification. You are not an observer, you are a participant in the ritual of submission to Roman authority. This architectural propaganda was strategically placed for inescapable public consumption. Triumphal arches were almost never built in secluded places. They straddled the most important roads, at the very heart of the city's ritual and daily life. The Arch of Titus, for example, was erected on the path of the triumphal procession itself. Every returning general, every foreign ambassador, and every common citizen walking the sacred way had to pass beneath its shadow. The message was unavoidable. It served as a constant stone reminder of the consequences of rebellion and the rewards of loyalty. For the conquered Judeans living in Rome, the arch was a permanent monument to their defeat. For the Roman citizen, It was a reaffirmation of their world's unshakable order and the divine right of their emperor. The arch was more than a monument. It was a psychological tool, engineered to inspire awe, fear, and obedience simultaneously. Its lessons carved not in perishable scrolls, but in stone meant to last as long as the empire itself. And so we see that the echoes of Rome are not confined to museums and history books. They resonate in the very skeleton of our modern world, a direct lineage of engineering DNA passed down through the centuries. That transfer of knowledge, however, faced a near total blackout with the empire's decline. For hundreds of years, the secrets of the arch, the formula for self-healing concrete, and the principles of large-scale aqueducts faded into obscurity, preserved only in fragments of texts and the silent, crumbling ruins that dotted the landscape. It was during the Renaissance that THIS, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, this sleeping giant, was reawakened. Architects and artists, looking back to the classical world for inspiration, began to seriously study the monumental relics around them. Filippo Brunelleschi's daring dome for the Florence Cathedral stands as the ultimate testament to this revival. Staring up at the Pantheon in Rome, he wasn't just admiring its beauty, he was reverse engineering its principles. He understood the Roman concept of a double shell dome and the use of a lighter, brick herringbone pattern to manage tensile stresses, adapting these ancient secrets to create his own masterpiece, which remains the largest masonry dome ever built. This was not mere imitation. It was a conversation across time, where Roman genius provided the foundational vocabulary for a new era of architectural ambition. The principles of the arch and the vault, so brilliantly perfected by the Romans, became the fundamental grammar of Western architecture. Walk through any major European city built before the age of steel, and you are walking through a world Romans would recognize. The grand railway stations of the 19th century, like London's St. Pancras or New York's Grand Central Terminal, with their soaring, arch-filled train sheds, are direct descendants of the Basilica of Maxentius. The arched windows and doorways of countless government buildings, libraries, and universities are a conscious homage to Roman stability and grandeur. Even the very layout of our cities, with their grid-like street patterns and centralized public squares, can be traced back to the rigid, efficient plan of a Roman military camp, the castrum. This was a template for order, designed to impose civilization onto any terrain, a concept that guided the development of new cities across the globe for 2 millennia. Perhaps the most urgent lesson we are relearning from the Romans today lies in the realm of sustainability and material science. For decades, our modern approach to construction has been defined by planned obsolescence and carbon-intensive materials like Portland cement. Now, as we face the challenges of climate change and crumbling infrastructure, scientists are looking back to Roman concrete with a sense of profound respect. The discovery that seawater actually strengthens their concrete rather than corroding it has sparked a revolution in materials research. Laboratories around the world are now actively trying to replicate the pozzolanic chemistry that creates self-healing minerals like aluminum tobermorite. The goal is to develop new green concrete formulas that are not only more durable, but also require less energy to produce, since Roman concrete cures at lower temperatures. By studying the nanostructure of 2,000-year-old samples from the harbor of Caesarea, we are essentially being schooled by ancient engineers on how to build structures that can last for centuries, reducing the constant and environmentally destructive cycle of repair and replacement. This philosophy of resilient, long-term thinking extends beyond just materials. The Roman approach to water management, with its gravity-fed aqueducts and sophisticated sewer systems, is a model of energy efficiency that we are only now fully appreciating. Their entire water network operated without a single pump, relying solely on a masterful understanding of gradient and flow. In an age concerned with energy consumption, the passive, elegant efficiency of the Roman system is a powerful inspiration for modern sustainable design. Furthermore, their use of hypocaust heating, which radiantly warmed floors and walls, is a principle that has seen a major resurgence in modern energy-efficient homes, proving far more effective than heating empty air. The Romans engineered for permanence in a way that modern economics often discourages, but their legacy proves that building things to last is not just possible, it is ultimately the most efficient and sustainable path forward. The true, enduring secret of Roman engineering, then, was not merely a collection of techniques, but a mindset. It was a boundless confidence in the power of human ingenuity to overcome any obstacle, whether it was a mountain range, a raging river, or the very passage of time itself. They looked at the world not as it was, but as it could be, and they possessed the practical brilliance to turn that vision into an enduring reality. Their structures were not just feats of engineering. They were acts of philosophy, stone manifestos declaring that civilization could be built to last. So the next time you turn on a tap and receive clean water, drive on a highway, or simply walk through a grand archway, take a moment to recognize the invisible hand of those ancient builders. Their secrets, once lost, are now guiding us toward a more resilient future, a silent partnership across the centuries reminding us that the greatest engineering is not that which impresses for a moment, but that which endures quietly and steadfastly for millennia. And so our journey through the workshops and wonders of ancient Rome draws to a close, but the legacy of their engineering genius is anything but a silent ruin. We have walked with them as they turned volcanic ash and seawater into a living concrete that grows stronger with time, a self-healing material that continues to baffle our modern scientists. We have stood beneath the impossible dome of the Pantheon, a structure that cheated gravity through a masterful recipe of progressively lighter stone, proving that their understanding of physics was centuries ahead of its time. We have traced the path of aqueducts that marched across continents, guided by tools so simple yet so precise they could map a drop of just a few inches over a mile, bringing the gift of fresh water to a million people. From the hidden hypocausts that warmed entire cities from the ground, up to the brutal efficiency of the ballista's torsion springs, each secret reveals a civilization that saw no problem as insurmountable. What is perhaps most astonishing is how these ancient solutions speak directly to our modern challenges. In an age of crumbling infrastructure and disposable construction, the Roman philosophy of building for eternity offers a powerful alternative vision. Their concrete, strengthened by the very seawater we avoid, points the way toward more durable and sustainable materials. Their gravity-fed water networks, operating without a single pump, are masterclasses in energy efficiency. Even their approach to crowd control in the Colosseum, with its brilliant vomitoria, informs how we design stadiums and public spaces today. The Romans were not just builders. They were master problem solvers whose ingenuity was born from a unique blend of ruthless practicality and breathtaking ambition. They refused to be limited by the landscape, the sea, or even the supposed laws of nature, constantly pushing the boundaries of what was possible. These were not isolated flashes of brilliance, but the result of a systematic culture of innovation that valued applied science, meticulous craftsmanship, and long-term thinking. The anonymous engineers who planned these projects thought in terms of millennia, not fiscal quarters. They left behind a world shaped by their vision, a foundation upon which our own civilization has been built. The next time you drive on a road, walk under an arch, or enjoy running water, remember that you are experiencing an echo of Roman ingenuity. Their secrets, once lost, are now being rediscovered, not as dusty relics, but as vibrant sources of inspiration for a future that demands resilience and wisdom. Now, I want to hear from you. After exploring these incredible feats, which Roman engineering secret left you the most amazed? Was it the mysterious, self-healing concrete of their harbors, the logistical miracle of their mobile invasion ports, or the terrifying precision of the Antikythera mechanism? Share your thoughts in the comments below. I rate every single one. If you enjoyed unraveling these historical mysteries with me, make sure to subscribe and hit the bell so you don't miss our next adventure into the forgotten corners of history. Thank you for watching.